We are still talking about light, but now we're going to learn a couple of terms associated with it. It's ionizing and non-ionizing radiation. We're going to learn what that means, how it relates to light, and of course bring it back to our main goal, which is helping to understand our ability to send and receive like Instagram messages, things on our phone. I really like this topic because not only are we learning physics and applications to real life technology, but also there's a lot of misconceptions when it comes to light and some of this technology, and this is a good way to help dispel some of those rumors, some of those myths. I have this meme. This is going to be, I think, funnier at the end of this video. I'll come back to this idea. But think of the classic banana phone, right? All right, we're going to come to that a little bit later. Now, here is our big question for this unit. How do you take, send, and view a snap? As I talked about, we've covered this. We're getting into this right here, the mechanisms that are involved in sending information. Think of Wi-Fi and Bluetooth, 4G, LTE, all that stuff. Okay, we're still learning the mechanisms that actually are going to cause these signals to be sent from one device to another, but we're going to look at a broad approach to this sending information in terms of the light that's involved and what that has to do with like your safety. Okay, still haven't touched upon this yet. That's in the future. Okay. This term radiation. To be honest, I've used that term a little bit throughout class. We talked about how it's something that's coming from the nucleus of an atom. Really, radiation is a form of energy that's either going to be electromagnetic waves, which are light waves, or as moving subatomic particles. We saw that term radiation for alpha and beta. A lot of times when scientists are referring to radiation, well, it's actually a pretty broad term. They're focusing on high energy particles or high energy light waves like gamma that cause something called ionization. But to be honest, remember, here's our $1,000,000 word or our $1,000,000 term, electromagnetic radiation. What does that mean if you strip away the fanciness? It's light. Okay, so certainly kind of in pop culture or in regular dialogue, radiation has this connotation of like high energy stuff, but really radiation is referring to light. Also these alpha and beta particles, electromagnetic radiation, electromagnets, remember those are light waves, that's referring to light. So you're going to see these terms, but they're not really any new terms. They're still referring to either particles or, especially right now, light waves. Okay? Now, let's figure out what this term ionization is. And to start, let's look at the prefix, ion. Now, if you haven't taken chemistry, this might be totally new, and that's okay. An ion is an atom or molecule, though we'll focus on atoms. It's an atom that has an unbalanced number of positive charges and negative charges. If you remember, I kind of hate this diagram, how they show it, but it'll do, I guess. In the nucleus, in this green, we have those protons. And then we have electrons that are orbiting on the outside. Okay, an ion is not when you have an even number, like 2 protons, 2 electrons. You would not call that an ion. If something has more electrons, look at this, I have 1 more electron, you would call this a negative ion, or you would call it an anion, but we're not going to use those terms. You could also have more protons, more positive charges than negative charges. That's also an ion. So an ion refers to an atom that has an unbalanced amount of pluses and minuses, either too many negative charges or too many positive charges. Okay, and ionization, well, that probably then makes sense that it's the process of how you get this. And really our focus is the process when it's coming to light and ionization, the process of how atoms might lose an electron. Right here, it looks like something happened. If things are nice and balanced and there's 2 protons and 2 electrons, something happened right here that removed an electron. So ionization is the process by which an atom or molecule acquires a negative or positive charge by gaining or losing electrons. But we're really focusing on this latter, losing electrons. Something is making this electron fly out. Here's a pretty decent image just to get us started. It looks like we have energy coming in. Here's our atom, and an electron, which is in this orbit, it goes flying out. My first question to you, it's just a hypothesis. Think of this diagram and think of the video we just watched before about absorption. what do you think is involved with an electron that's maybe moving or is maybe reacting to energy? What would be your guess as to what would be causing this? What do you think? Give me a sentence to two-sentence guess. Okay, what's going on? Let's figure out what's happening. Okay, so how do electromagnetic waves, whether they're radio waves or gamma waves, cause ionization? Let's go back to what we saw in our last video. We learned that these electrons are in different orbitals, but really that's referring to different energy levels. You could be here. Here's kind of a nice low energy level, just like if I'm on the bottom floor of a building, or I could be at a higher energy or an even higher energy level. Just like I could be here, or I could be here, or I could be here. I could be at different energy levels with gravitational potential energy heights, and I can have different atomic energy levels with these electrons. How do I go from one energy to another? I need to gain energy, and that makes sense here too. But remember, for electrons, there's very specific, quantized energy levels, and I need a specific amount of energy. If I need a specific amount of energy coming from light, from our equation, that means there's a specific frequency of light that I need. So that's true. These electrons always need very specific energies, with one exception. Imagine I strapped on like a rocket pack, and I was given so much energy from that rocket that I didn't go here, or here, or here, or here. I had so much energy, I launched into outer space. I left the Earth and that gravitational potential energy from the Earth. There's one exception to this rule of needing very specific energies. If that electron gets enough energy to actually entirely leave the atom, leave that attraction from those protons in the nucleus, well, an electron will absorb that energy. We call it the ionization energy. It's the minimum energy needed to ionize an atom, to make that electron go flying off. Remember, think of those photons, those particles, right? That kinetic energy that's knocking electrons away. So normally you need very specific energies, okay? Unless you hit that bare minimum, kind of an energy greater than, say, this one, so that the electron would no longer even be bound to that atom. It goes flying away. So you need a certain amount of minimum frequency light because that would give you the minimum energy. So how can we ionize an atom? By giving it enough energy and giving it therefore a high enough frequency of light that's going to make that electron get stripped away. I often use that term. You're stripping electrons away by shining high enough energy light at it. Okay? I'm going to leave here and I'm going to go back to that animation I showed you before. As a reminder, normally if I have this electron right here, I need very specific energies in order to have it move to higher energy. Green doesn't do anything. Okay? Even if I go to a high energy light, if it's not a specific high energy light, oh man, nothing. This energy right here would be like energy to get right here. But that electron can't go right here. It has to go either here or here. So just because it's high energy doesn't mean it's going to get absorbed unless you exceed this energy. If I can give the photon, or if I can give the electron enough energy to leave this spot, then it gets ionized. It gets stripped away. It's like it's free. So here I have that preset. This is the highest energy the electron will absorb and still be bound. See, it jumps way up here to that highest energy level, and then it kind of cascades downwards. Okay, and remember, it emits light as it cascades. It absorbs light, and then it starts reflecting or emitting that light as the electron jumps back down. But if I move my slider to be at a higher energy than that, so now I'm exceeding the energy of this highest level. Let's fire that photon. Ooh, it was a little tough to see. This animation has its drawbacks, but that electron was just kicked away from the atom. Now, we're kind of going to ignore this second half. What's happening here? Maybe you saw an electron float down. Free electrons might get gathered. They might get captured by this atom, and then they're rejoined. But if I fire energy that's more than that highest level, Ooh, that electron just floats away. It's no longer bound. That's me meeting that ionization energy requirement. Okay, so imagine this doesn't say energy. Imagine this says like ultraviolet or gamma wave light. It has to have a high enough energy and it kicks electrons out. Okay, so here's that spectrum again. But now this spectrum has a new detail. It has a label showing the types of light that are not ionizing. They can't strip electrons away. And they have light that can strip electrons. Now, how much energy you need, it's going to be based on the atom, like how much attractive protons there are, how many repelling electrons. But even with the laziest, the least grippy atom, you need a certain amount of energy. And again, by this equation, if you need a certain amount of energy, you need a certain frequency of light. This right here is the limit. This right here is the barrier. You have to have at least ultraviolet light to strip away electrons. I don't care how much microwaves you're shining at atoms. Doesn't matter. Remember that photoelectric effect? Whether you're shining it for a second or years, microwaves don't have enough frequency, therefore don't have enough energy to cause ionization. This is the bare minimum. Ultraviolet kind of straddles these two categories. Some ultraviolet light does not have enough energy, but some does. And this is the type of light that can cause like sunburns. Okay, so if I want to be able to strip electrons away, I at least need this type of light, gamma, X-ray, or ultraviolet. Anything over here in this red section doesn't have enough energy to, frankly, ever ionize those atoms. Now, why is this considered dangerous? Why could ionizing light be harmful to people? Why do we say gamma waves and X-rays and ultraviolet, some ultraviolet, can be harmful? It has to do with what atoms might be ionized. Imagine that little simulation we saw. Imagine that was an atom in your DNA, one cell of DNA in one atom of DNA in one cell in your body. Well, of course, how atoms and molecules form bonds is by sharing electrons. Bonds are formed based on how many electrons are present. If you damage one of those atoms, if you strip away an electron, well, maybe it's not going to form those atomic bonds it would normally. And it's possible that if that's happening at just the right spot, that might mess up your DNA. And in particular, when DNA is replicating. Because imagine you messed up like one of these cytosine cells, okay, or collection of molecules, really, collection of atoms. Then when the DNA goes to reproduce, oh my gosh, if that damage happened right here, maybe this is a piece of the DNA that says, stop replicating, right? Because DNA is all code. It's like a computer code. It tells cells like what to replicate, how to replicate, when to start, when to stop. Imagine that we just damaged the stop piece of the DNA. Well, when this starts replicating, now the cells aren't going to know when to stop. And then the cells are going to replicate and replicate and replicate and replicate. Do you know what it's called when you have cells in your body that don't stop replicating? That's what cancer is in a very general way. Cancer is when you have cells that have this runaway replication process. They don't stop. So therefore, that can cause growths and pressure and cause nearby things to start malfunctioning. So this ionizing light can be very dangerous because if it damages our DNA in the right spot of our DNA, well, it can cause things like cancer. That's really the danger of this ionizing light. So ionizing light, UV light, X-rays, and gamma waves, those are light that has enough energy, enough frequency to strip away those electrons. And if that happens at just the right atom in just the right cell of some organic material, well, that could start causing biological problems. These things are all non-ionizing light. So because X-rays are ionizing, that's why when you go to the dentist, they put a lead vest on you because they want to limit how much X-rays are actually hitting parts of your matter. You shouldn't be afraid of X-rays still because this is still really a probability game. You getting one X-ray, the odds of that light hitting that specific atom in that specific cell that's going to eventually cause cancer, millions to one. Okay, so still go get X-rays. But imagine you're an X-ray technician and you're giving X-rays 50 times a day for 30 years. Well, that could add up. That's why the x-ray technicians, those people in the dental offices or the hospital offices, they leave the room, right? Because for them, getting x-ray after x-ray, that's just going to increase the chance of that ionization happening. Now, here's the key idea, and this is where we're going to get into some misconceptions. These 4 types of light cannot ionize. They cannot strip away electrons, period. And therefore, there's no chance of this dangerous cell replication, this cancer going on. So I want you to think about things that use this type of light. Microwaves use microwaves. Radios, of course, use radios in your home or in your car. And then all of our modern technology, whether it's Wi-Fi or Bluetooth, 4G, LTE, your phone, those things are using combinations of microwaves and radio waves. None of these things have enough energy to strip away electrons. None of them can cause cancer. There's no known physics mechanism that can cause cancer the way we know gamma, X-ray, and UV light can. So if you had like an uncle or someone ever tell you, don't stare in front of that microwave, they're wrong for several reasons. But certainly microwaves cannot give you cancer. And let me remind you, if you are concerned, or if there's like a relative of yours who's concerned about these things, well, visible light has more energy than all of these. Everything I have on this screen is radio and microwave. If you're afraid of these things, you should be absolutely terrified of all the light that's all around you, the visible light, because it has more energy. This should be more dangerous than this because it has more energy, right? So there's a lot of misconceptions. It has to do with what type of light has the ability to strip away electrons and potentially cause cancer, and what type cannot. Now, sometimes I'm just about done. I know this is a long video. I bet you can suffer through it. Okay? Sometimes this is used to our advantage. We might want to use X-ray and gamma waves to destroy cells on purpose. Imagine someone has cancer or a brain tumor, especially if it's a difficult place to cut in and remove. Well, if you use gamma waves, which remember can ionize and can damage cells and can maybe stop cells from reproducing, you can use this radiation to actually focus in on those cancerous cells. So gamma radiation therapy is often used to help patients, knowing that certain types of light can damage or strip away electrons, which can damage cells and can affect that replication process. Okay, so sometimes this is used to our advantage. Okay, so ionizing energy, ionizing radiation, it's high energy forms of light, which is what we've been talking about for the most part, and what it can do is it can separate electrons from atoms, and that can mess up things like DNA replication. Okay, here it has it affecting chemical bonds. So going back to my very first image on that slideshow, ironically, if you remember bananas and you remember radioactive potassium, ironically, I'd say it's more dangerous to pretend holding up a banana as a phone than it is holding up an actual cell phone. And you'll get practice being able to explain that in at least a couple sentences in our upcoming practice. I know this was a long video, but this is an important topic and it has several layers to it. Okay, but that's the end. Thanks a lot for watching.